First of all, I would like to thank Venus and for facilitating this week because it is very important for me to read this quickly, and then I like to thank everybody for coming here and giving me this opportunity to present our work. The title has already told, so it's written with my postdoc supervisor and Fred, and this is background paper which is in communication. Okay, so
Yeah.
So I would like to start by giving some introduction and motivation, and after that I will give a better outline of the talk. So we'll start from KD superstring theory. We'll take the low energy limit. And in low energy limit, we have the KD supergravity and plus some stringy ingredients at the lowest order, which are like O planes and branes, D branes. And we will compactify to get the 4D particle physics. So schematically, this is the procedure. Ideally, you want to start with the KD superstring theory and then compactify and then take the low energy limit. Most of the cases, these two procedures common, but there are examples they do not. But in any case, for this talk, we take the first two. And we will focus on a specific superstring theory, which is the type 2B superstring theory. Okay, so this is one slide for the system, just to show the action. So in low energy limit, you have the type 2B supergravity pseudo action. Like this is good for deriving the equations of motions for the fields. The fields are the metric, Kendi metric, the Calderon field, the dilaton and some form fields. And the quantity, the field strength that appeared in the action has been written here. Although I will soon switch to our variables, which are axiodilaton and the G3 flux. So these are the variables, and F tilde 5, these will be used next onwards. The action can be rewritten in terms of that, but I haven't written. So on top of that, we have action for local sources like D planes and O planes. This should be, I would point out that this should be important for getting the background. But since we are studying, we are not studying moduli for these brains coming from like for us, they just give the background. Once the backgrounds are fixed, you will soon see that they will not be much important in this work. Okay, so now some few statements about what is there. So in TLD type 2B supergravity, inclusion of D branes and O planes and which GKP backgrounds. So their features are word 10D space time. So there is a 4D Minkowski's part which is word. Like there is a y dependent, y is a extra dimension coordinates or internal manifold or whatever you like. So there is a dependence on that. So this is the word factor. And then there is a Ricci flat manifold once you pull out some factor. So this G tilde is the Ricci flat manifold. I have taken some notation like not. It's because soon we will be taking fluctuations around the background values. So the not denotes the background values basically. So there is a Y factor. I will discuss when I will go into details here. But in the solution, it is not fixed. It can be anything. Okay. So if you solve the 10D equations of motion, this Y factor is given in terms of the 3-form class in the GKP background. And there is a quantization for F3 and H3. which is in units of alpha prime, they are integers. Therefore, the work factor goes as alpha prime square. In the large volume limit, like what people basically do for phenomenology, the effective action of the work compactification becomes a direct product compactification in large volume scenario.
Dedim wypadne elektryk. Myślałem, dedim, jo?
Gdy.
Bude něco na jízdě po přepojení elektrického. Tak nevím, jestli vás mám nechat, až to dokončíte celý ten...
No to máme jako do 12,
Jako až po 12.
To by bylo lepší. Jako kdyby
Takže
to bylo...
třeba o půl jedné řeči.
Jo,
Už to nejde.
Jo, to by bylo
správně na obchod.
He wanted to turn off the electricity. Oh. Told him to wait till 12:30.
For the whole, still they were just.
No, for this. For this room. Some rooms too.
Okay, so in large volume limit, the effective action of a direct product compactification is a good approximation. So from there, like if you want to do precision string phenomenology, it's clear that work factor and flux corrections are always alpha prime square in for the 4D physics. So whatever we will be computing, if people want to do precision string phenomenology, it would help them to compute corrections. However, our procedure is such that even if the warping is very strong, like one can give explicit results. Okay. So the GKP background can be defined by a set of parameters yielding a family of 10D solutions. So it is not a particular solution, there is a family of solutions. And once we compactify, they usually lead to massless fields in 4D. And we have to compute the Moduli space metric even in the case of strong warping. So that's our aim. And our focus should be the geometric moduli. So which are the modular space of the Calabi-Yau manifold given a background. If we take the deformations, which are Kähler and complex structure deformations, we want to some parameters, set of parameters will come from those deformations. We want to dimensionally reduce those moduli. This has not been done previously. Yeah, and I should mention here that not all, all the Kähler deformations, but not all the complex structure deformations are in the family of solutions. So if you allow some of the complex structure deformations, they might not be the 10D solutions anymore. So we come to this point, but roughly this gives the motivation. Aim what we want to do. And earlier dimensional reductions focused on the universal volume modulus, so we will not do it in this one. Actions coming from the form fields, D3 plane position moduli, like for us, D3 plane or the O3 plane, they are fixed, they are not moving, but if those have been dimensionally reduced, like if you allow those differences. Okay. So I should mention that in a different approach for the the Kähler potential for the geometric Kähler moduli has been derived from a combined consideration of expected n equals to 1 Cauchy properties of the effective theory and the structure of 10D vector. Therefore, if we can compute the metric for the at least for the Kähler deformations, we can check with Martucci's result that if we agree or not. So disclaimer, we agree, okay. However, this requires Cauchy properties. So the some sort of Cauchy should be there after compactifications, and this also use SCFT actually. But our method only rely on the 10D equations of motion and can be applied whether the background is breaks Cauchy or not. And in fact, we have not done, but one can apply these kind of methods to more general compactifications like non-Calabi-Yau compactification. So these are the advantages in the methodology. And for the complex structure sector, whatever be the result, it's the first time in the literature. So, okay. So before going into details, I just want to show why one slide for why what flux compactifications. It's nothing but the Ramsden-Sundam scenario for the string theory from 10D to 14 instead of 5D to 4D. So the relations are there. This side it is the 4D plant mass, and this is the fundamental string mass, but there is a work volume. So since we do not need to go to very large extra dimensions, because if we take strong working, it is already very large, and the fundamental string mass can be lowered down below this. So this is exactly like RS scenario. On top of that, the direct product compactification, there are many more moduli. But flux compactification, which will show the work factor, this stabilizes many of the geometric complex structure moduli. This I will explain in some. Okay, but whatever unstabilized, the massless moduli in 4D are important for cosmology because non-perturbative conditions could stabilize all other moduli giving mass, and they find phenomenological applications in cosmology. And so our computations are for massless mode, so they will, like the work factor corrections we get would be helpful for decisions too. Okay, but I will not talk about phenomenology in this talk. Okay, so this is the outline for the remaining talk. So I now explain the geometry moduli space of GKP compactification. Then I will talk about the dimensional reduction to get the moduli space metric and discuss some outlook. Any questions, or I should just start the second part? Okay. So this is the GKP background written by some law. I have written it here. So it is the word metric. I have explicitly written the F tilde 5 answer, like for the background, and some properties G3 should hold, and the axiodilaton is taken as constant. There is more general GKP background, where these can be varying over y, the extra dimensional coordinates, but we'll stick to that. And this is also like most, widely explored in the string phenomenology, because like this is the identical limit of F theory. And on top of these, the work factor is chosen by the fluxes. So usually they are quantized by set of integers in units of alpha prime. So given those set of integers, solving a Poisson equation on the internal manifold, Calabi-Yau manifold, one could in principle solve this. And I should mention here the importance of the contribution from local sources, because if you integrate this over the extra dimension, the internal manifold being a non-bounded one, this side is 0. This is positive contribution, so therefore it should be cancelled. Some negative contribution should be there. So these are the O3 plane contributions, and that's why we need identical plane. So and this is the background. Okay, so F tilde 5 is self-dual as written, and this is constant coming from type 2 string theory. Also to ensure the closure of plane issues. Etc. G3 features component only on the compact directions on the internal manifold. It is harmonic and it is imaginary self-dual. So with respect to the background Calabi-Yau. So these are the properties of the GKP background, and this will be very important for us because I will explain now. So we'll consider linear metric fluctuations of the form these. around the background Calabi-Yau metric. For timing, take U as a constant parameter. So we want to depart from the background by a constant parameter and see whether we can find a continuous solution or not. So, but we will ensure DC flatness at linear order. We will also preserve the onward volume because we do not want to model volume modulus. It has been dimensionally reduced. So specifically, we want to deal with the other non-volume deformations like non-volume Kähler deformations and complex structure deformations. On top of this, we should put a gate choice when U is constant. But we will see it is possible using deformation invariance of the 6D. But we will see that for us it is not a gate choice when we will allow U to be dependent on X later. But we will find it as a constraint. I will talk about how to derive constraints and why they are important. Okay, so if you satisfy these three, they say that this can be written in terms of specific harmonic forms. Harmonic 1-1 forms give the Kähler deformations. Harmonic 2-1 and 1-2 forms complex structure deformations, and there is U and U bar associated to this because they are complex numbers. So counting is like 1:2. And then they form the moduli space of Calabi-Yau, but not all of them are moduli space of the GKP compactifications. It is because when we study these deformations, we further want to go from one GKP solution to another because we want to find we want the deformed 10D system to solve the 10D equations of motion at linear order. Because of that, I mean by this kind of deformations, this will allow only a few of them. Those are the moduli space of GKP compactification. So, once you deform by these, you also in response have to fluctuate the work factor, the Y factor, and the axiodilaton. Okay, I should also say about the Y factor. The Y factor is as far as equation of motion constant, it's anything, but it can be chosen so that the 4D Einstein inversion is properly normalized. It's a choice. So I could have written a formula for that, what we are taking, but it's in the paper. So okay, so we should allow some fluctuations. Also in the 3-form flux through some potential eta 2, the 5-form flux. So why so? Because we want the deformed 10D system to satisfy the 10D linearized equation of motion. So if you only fluctuate these, if you do not adjust them, they will not satisfy the linearized equation of motion. So these are the fluctuations can be engineered. On top of that, since we want to go from one GKP background to another GKP background by this parameter Q, the G3 part of G3 should be imaginary self-dual again because that is the feature of GKP compactification, and we are looking for the moduli space of GKP, and that is restrictive. So we get some conditions. I will refer it as linearized density condition. In one side, it takes the shift in the 3-form flux, also through eta 2, and also it have the.
Sorry, what is the I in this?
Okay, sorry. This is the imaginary self-dual. Yeah, sorry. This is the relation. And if we record that the deformed system, I mean, part of system is again a solution of GKP kind. Like part of G3 must be ISD. And in one side, it has the fluctuation of the axiodilaton and the eta 2 like G3 shift. And on the other side, it is the action of the star operator on G3. It is because once we linearize star operator, the external manifold is now fluctuating. So there will be a fluctuation in the star operator that should act on G3. And that is giving me some of 3. We have called it W3. Immediately, like certain properties of W3 can be proved using complex geometry. For example, W3 should be anti-imaginary identity. Like the same relation with a minus sign for W3. But I'm not going into those details, but one can prove certain properties of W3. For ISD, imaginary self-dual G3, only allowed components are harmonic 1, 2, and 3, 4 components. Therefore, one can judge from here that whether this equation can be satisfied for the Kähler moduli or the complex structure moduli. As I said, that not all are moduli of the GKP compactification. At this stage, we should judge that what are the in the moduli space, what can be satisfied, which deformation satisfy this linearized energy. So I am stating the results. Any Kähler deformations like the linearized deformation can be satisfied and delta tau must be 0. It is because this equation has a Hodge decomposition structure. In this side, it is exact. This can be written as a co-exact, and this is always harmonic because it's the background G3. And any harmonic component of W3 should match with that. And the components for the Kähler deformations that can generate here is not of this form. So delta tau must be 0. So that we have found. For the complex structure, depending on the background value and the given complex structure deformation, the linearized deformation can be satisfied only if the harmonic piece cancels with this and with this piece, and there are possibilities. We have explicitly found examples and give it is possible to cancel this because for complex structure deformations, one can generate here harmonic 1, 2, or 3, 0 piece, unlike the Kähler deformation. So they can cancel this. So this kind of relation can be satisfied. And we will refer to these complex structure deformations, flat complex structure deformations. And since delta tau is non-zero, because this cancels with that, and delta tau should be non-zero. So also like tau varies. So tau also remains, the axiodilaton also remains flat in these cases. So these will be in our scope of discussion. So these are in the moduli space and all Kähler deformations. However, there are complex structure deformations given a background G3 class. They violate the linearized deformations and they are the stabilized one. And that's what I was telling earlier, that task compactifications stabilize some of the complex structure moduli. It was earlier believed that they stabilize all of the complex structure moduli, but there are cases where some of them are not. They are moduli of the GKP compactification. But the massive moduli, which is stabilized, will be beyond the scope of current part. We will focus only on the Kähler and flat complex structure moduli. So, okay, solving linearized 10D supergravity equations, we have fixed the y-dependent functions. I'm not giving details, but I will show some soon. And I am talking about geometric moduli, like the deformations of the Calabi-Yau. I should also say that what are some other moduli, so that still it is one GKP solution to another. So those are if you vary the core formulas by some set of parameters. In this fashion, where these are the basis of harmonic 1 forms. They are also moduli of the GKP compactification. They have been dimensionally reduced earlier. At some point, we will take those results to combine with our result to write the reaction in a nice fashion in a later stage. Okay. So this is the end of second part. I will now dimensionally reduce this moduli, but you have questions at this stage. Even okay. So I will describe some of the methodology and The second section and the third sections are the main part of this work. So I will describe this methodology in some detail. Now we have to allow the edge dependencies in the variations because they will be our code fields after the dimensional reduction. And the y-dependent part in the metric fluctuation will be either a Kähler deformation or a flat complex structure deformation. So we need to, since we are allowing x dependencies in the parameter, we need to find correct Kähler fluctuations. I will explain what do I mean by correct. And then we have to substitute this fluctuation in the Kähler action and integrate one. So this is the idea of dimensional reduction. So I have written here our answer. So this I will explain through this example only. So the answer is this. Since you have now S dependencies, there are derivatives of A. Those are the extra terms compared to the previous case. You can see that there is off diagonal compensator, one form field B in the metric, and so as if tilde phi has been modified to the derivatives of U, G3 is also. So whatever is required, like we have engineered. If tilde phi is again, the self-duality has been maintained. And expanding U and its derivative, the zeroth order terms coincide with the GKP backgrounds. If you want moreover suite of the x dependence, it is exactly the previous fluctuation I showed for the when U was constant. Okay, so there are some new terms. And we want to satisfy the Kähler Einstein's field equations of motion for form fields and Bianchi identities and linear order. And schematically, we get these four kinds of equations. So one is, I will start from the fourth one. One contains box operator of U equals to 0. This we will not satisfy. Why? Because we want to derive an action for the 4D fields, and these are massless fields. So this should be the 4D equation of motion. So after deriving the action, we want this equation coming from the order-Lagrange equation of the 4D action. We do not want to impose this. If we impose this offset, the action vanishes. So we do not want to impose this, but we want to impose the others. And then we want to arrive at an action which gives the 4D equation as the equation of motion of the 4D fields. And this is the massless 4D fields. Okay, so among these three terms which are proportional to U, we are setting them to 0. It is because this has been done in the previous section also. The deformed tendency system depends on the Moduli space of GKP compactification. Like when you switch off the H dependence, they are the only equations that we have already discussed earlier. Well, I have not discussed the solutions. But if you just, from here, if you just switch off the H dependencies, you will reproduce the earlier result and they are already maintained because we want to stay in the Moduli space of GKP compactification. Okay.
So I thought those are fluctuations.
Which are?
The U's.
Yeah, U is fluctuation. U is the US. See that these are the y-dependent parts. The dot parts. Yeah.
So if you set U to 0,
I am not setting U to 0. I am setting the coefficients to 0. Sorry. This bracket part is 0, not U to 0.
This is just like a way to organize the equations by using U.
This you can see like this is the organizations like what we have written. So whatever is involved, we are setting to 0, not U.
but wouldn't that mean the linear fluctuations vanish?
The linear.
Because the term proportional to U, I don't directly see why would they vanish.
This is not something. So okay. First of all, these are the KD equations of motion. They should be satisfied. I have arranged just. I have plotted the fluctuations. I have put in the KD equations of motion, and they are the equations of motion. Now, in principle, if you are looking for solutions, you should satisfy all four of them. But we are relaxing this, we are maintaining this, but how? Not setting u to 0, but setting the coefficients to 0. And these should give, because they are they depend on these quantities. And setting these to 0 will give us like a constraint on them. And they are required because the default system should also be like satisfying the equation function. So they are required. So they are not also abnormal. Okay. So I will explain something more about why we are setting to 0. There are two approaches. One is the Hamiltonian. Okay, I will explain this in the next slide. Okay. So now if you satisfy these, the first three kind, whatever is written here, thanks for mention this, that these are the factors, they will restrict these functions. Okay, let me explain this anyway. So if we restrict this way, then only the like they indicate that diffeomorphism invariances are maintained, otherwise not. Because once you plug these fluctuations, first of all, to integrate one, you need to know what are the fluctuations. Otherwise, they are arbitrary functions, so you can't integrate arbitrary functions. But if we have these functions known, they satisfy certain equations because of this, and then we can plug them in the deviation and integrate one because the functions are now known. So that's what I mean by cutting, because these fluctuations are not arbitrary, they satisfy certain equations. And therefore, we know those functions and we can, in principle, integrate them to get the potential. But once you integrate, of course, it's written as a 4D Lorentz invariant way. So the 4D gauge invariants and etc. manifest. But there are 10D gauge invariances. Like 6D x and y coordinate would have been mixed. So there are formalisms on show that these constraints, if you allow these constraints, they whatever gauge choice you start with for the 10D action, they end up with the same 4D action. And another formalism is the Hamiltonian formalism, which I have less idea, but they say that it is in a constant system, and they build some Dirac notation for constant systems and etc. And they also make it clear that these are important. So there are two approaches, but I am more familiar on the gauge invariance side. But yeah, so at least this is what we are doing. Okay, so I saw some of the equations on this, which are common to both the geometric setting. Others for eta 2 or delta tau can be found in the paper. For example, for Kähler, delta tau is 0, but for complex structure, it's 1. So this we get as a constraint, like the covariantly transverse deformations. We get co-closeness of the eta 2 potential as constant. We get y factor does not change. Importantly, we get some Paulson equations for the work factor fluctuations and the one from field B1, which was the metric compensator. So these can be solved. We have solved it in terms of biscalar and bivector Giddings function. And there is a relation between bivector and bivector Giddings function that relates their derivatives. Using these, one can satisfy another constant which we got that commits divergence of this one form to the fluctuation. So whatever results we have written, we have actually solved all the constraints, and we are good to go with the dimensional reduction. So we know what are these functions. We can plug all these fluctuations and now compute the action. But in action also there is a organizing principle. I will just describe the schematically one, and the details are in the paper. So to work with the action, like schematically, you can consider a set of fields psi A, and then we have an equation of motion. This side I will call it equation of motion operator, which is equals to 0. So they are functionals of fields. Okay. So if we consider a classical background, they satisfy the equations of motion. And if you now take linear fluctuations around the background values, certainly whatever was the functional relation, they will also acquire some fluctuations. And they depend on the fluctuation in the fields and their derivatives. Now, if we plot these fluctuations in the action, like at zeroth order, we get a constant. Basically, the action evaluated at the background values. Linear order terms vanishes by the background equation of motion. At second order, we always get this. So, what is this is second order because it's first order in field fluctuation. This is also so. It's second order. So, this is the organization principle, and then we can integrate y. But right thing is that here schematically I said that I have to deal with the linearized equation of motion. That we have done for the KV supergravity already. In the previous slides to get the constants. So these are already there while computing the constants. We plug them in the above expression and impose all the relations we got and integrate y. There is a certainty regarding the Seaford fluctuation because our answer is self-dual. Once we that is required to solve the Kähler equation of motion. If we plug these self-dual fluctuations, like the F self-dual, they do not contribute anything. But there are prescriptions apart from like Ashok's one. There are prescriptions people are dealing with for this. So we took those. What we did, because of the self-duality, not all components are what it is called independent. Sorry, independent. We get only the magnetic components. It should be in quote unquote because by magnetic we mean mostly who has components on the extra dimensions. From the analogy like electric are on the diagonal on the first row, magnetic component magnetic components are on the like mostly x directions of Fij. So we kept only the independent fluctuations and we evaluate the action of these contributions and we multiply it by 2. So that's the prescription people used to work. There are other prescriptions also. Ultimately, those gives same answer, but we stick to this. But it would be also interesting to do this procedure in also sense formalism, I think. Okay. So I am showing you the result, the final result. After the integration, we have for our case, for the Kähler Moduli case, including the volume modulus and C4 actions. So recall that once we vary the metric, those are given by harmonic 1-1 forms, properly normalized, and they will generate some fluctuations in the metric, which is this is an equivalent statement like the Kähler form also get a fluctuation, but it is equivalent to like changing metric. And delta C4 we have allowed the actions, combine them, and especially one of the harmonic 1-1 form is nothing but the background Kähler form, which is written in terms of the background metric. It is nothing but the Kähler metric on the background, like G tilde I J bar dz I dz bar. I should have written it. So
There's a pen there if you want.
okay. So given so this is the background Kähler metric. The form is nothing but the Z bar J. So this is the background or given any Kähler metric, one can associate a true for which this is 0. I am using tilde or else for y direction, so they are all in the extra dimensional manifold. So and they are included in the basis when people write this normalized basis. So if you take the first direction along them, and the corresponding moduli gives the volume modulus. So here we have taken everything. People usually also combine U and V with by choosing a holomorphic variable for taking the 4D. That's given in the paper, but I am not showing here. Okay, so what appears here? The volume of the background of factor and some one form appears. They can also be found by. They are coming from actually eta 2. I didn't show eta 2 in the previous slide because it's not common results, but they can be solved by solving a Poisson equation, which is solvable. We have checked the solvability, and these are non-trivial because the source is this, and in a Calabi-Yau manifold, although this is harmonic and this is harmonic, but Lorentz product of harmonic forms are not harmonic. In most general Calabi-Yau manifolds, only one case I know is torus, where Lorentz products of this is harmonic, and since it is not harmonic, it's non-trivial because there in Calabi-Yau triple there is no harmonic 5 form. But since it is not harmonic, this is non-trivial, and this gives some non-trivial answers. This is the answer. So okay, I should now give some moment on explaining the implications of this method. So in a sense, we got a Moduli space metric which looks a quadratic action. It's a quadratic action, but we need the moduli dependence. That is useful. Like how the Moduli space metric is dependent on the field, like something schematically I wrote Gij, how it depends on the fields, and then I think del mu I del mu j. So the Moduli space dependence is implicit here. At least numerically it can be computed. How it is implicit? Because you can see that everything depends on the background values. For example, it depends on the background work factor, the background free-form flux, background axiodilaton, and implicitly on the metric. To choose the metric at a first and see which representative of the homology given a metric and harmonic also depends on this, because like harmonic means they satisfy some Laplace equation. Therefore, they also depend on this. So, idea is you start with in the to specify even first and the background, you have to be somewhere in the Moduli space of the Calabi-Yau to specify all the unit. You start with them, those you call U0, and do this computation. You record the value in front of that. You change them because all are suitable GKP backgrounds for any. You change them and then again do that and record this. But we have given the formula. These harmonic forms are dependent on the metric. So basically, changing the metric, everything changes. One can numerically solve this. And I am focusing on numerics because nobody knows the Calabi-Yau metric explicitly, except there are recent progress on the numerical parts. Okay, so in a similar way, we have obtained the 4D effective theory of flat complex structure moduli. I thought it's again some set of terminology, so I skipped the result. And it's there in the paper. It seems that it's a kinetic mixing between the Kähler moduli and flat complex structure moduli, which is a new thing. Like in the direct product compactification, they decouple. We could not prove them vanishing, but maybe some Calabi-Yau property and etc. could prove it. but at least the expressions we have written in the paper, and hopefully we at least good thing is that in the large volume scenario, where it should be the direct product compactification, they drops. So we are consistent. Okay, so I will now discuss some outlook which discusses these results also. So first of all, develop computational tools capable of calculating the Moduli space metric. As the background Calabi-Yau metric is varied over the Moduli space. And this would allow precision in phenomenology even in the case of strong modeling, because we have given explicit formula by Y factor is there is no approximation. So notably there are advancements for computing the forms and metric of the COI, so this should be like some sort of invitation towards them if they want. Yeah, so what is left is the dimensional reduction of the massive complex structure modeling, which violates the ISD condition. Like we satisfy ISD condition because we wanted to linearize the ISD condition because we wanted to stay in the modeling of DKT. But there are complex structure modeling like conical deformation modelers, they violate them and they actually get some pass even in 4D. And the first steps appear in this paper. I would say first step because they neglect. Like we have understood now that G3 should have achieved by taking linearized ISD, but they have no change in G3. I mean, this paper, although this paper claims to solve important issues like stability coming from like by Bela and Rana, they showed that there is some instability when you add anti-Giddings for conical deformation modelers, and this paper claims to solve that problem, and people are okay at least with the result. We also think that the result qualitative will not change, but we have to add these fluctuations and redo these and see. So hopefully that we'll be doing, and we have started looking into these. There is Kähler conjecture that suggests that there is an upper bound of the stabilized complex structure modeling for like Calabi-Yau reports with large Hodge numbers. So if there are more like complex structure modeling, only few of them are stabilized. Like there is an upper bound by Cox compactification, and that was I mean that is new. Like the GKP idea was that at least complex structure sectors are all stabilized, only Kähler are not, but now it is clear to the community that some are not. We have also found examples. But what is the upper bound? And they have some formula for that. It's called Kähler conjecture. Tests have been done using at the level of 40 directly in the effective field theory arguments like superpotential or period breakers. But what we got? We got a 10D analysis, we got a linearized condition, which is a 10D coming from 10D, and which just relates the Calabi-Yau geometry, our linearized condition. So our procedure is an alternate to attack this problem. So for example, for given a Calabi-Yau identifier and flux quanta satisfying these with some conditions like Kähler bound, determining which complex structure deformation satisfy our linearized condition poses a counting problem. And then we have demonstrated in the choroidal default in the recent version paper, and which agrees to our old work, but that work was based on the superpotential. But okay, also I should say that choroidal default, because they are not large H1 are not under the scope of the conjecture, but at least the counting problem is explained. And in principle, we can attack this problem using this our approach. We have like from the linearized condition approach. We have seen that our approach is equivalent to using the 4D superpotential, but it's an alternative thing. So it may give some insight to prove or disprove the conjecture. Okay. So all of these procedures are about the zero moves. But we know like the massless fields, even if it is the massive case like conifold is the lowest mode. But we know that these operators, the Laplacian has higher modes on the Calabi-Yau. Those are the eigenvalues. Those will be the Kalzakline modes. And do we have any satisfactory Kalzakline decomposition in word compactifications? There is first step in this paper, but apparently with word factor there, it's less understood. Like they have not included all the fluxes here, and also like they did not like have the massive mode clearly identified because they got some mass matrix. They have interesting results because of word factor. All the KK modes are worked down, so they are lower than the direct product compactification. So very useful implications are there also, which would be important for phenomenology. But we want to do it for more rigorously, and we have some idea. I am stating one problem. Finally, that's my one of like maybe coming 2 years. This can be attacked, but for right now I have to develop also this KK decomposition for word compactification with at least in the type 2B with all the fluxes. But once you have this, there is a problem like computer 3-level 4-dimensional amplitude in word flux compactification, where derivator is a modulus, like we said, right, axiodilaton is a modulus in our complex structural calculation. So we have already these cases obtained in both the work. And if we compute this, this will account for understanding of the classical Reggiani conjecture for 3-level amplitudes. Because like it has been listed in this 100 open questions by Minola. Because nobody knows that in word compactification if the amplitude goes faster than A square or not. But if we have a KK decomposition, at least for the 3-level amplitudes, we can allow the modes that can go and see that what are the sum rules. So there is a paper in the higher scenario, at least 5D to 4D they have done. I think this sort of say that yes, this conjecture is true for word compactification also, but it's RS, but at least in the string theory setup, whether it's can be there or not. Good to check. So, yeah, I want to stop here. Thanks.
I have a question. So you mentioned that the wild factor is important for the 4D Einstein term, right?
Yeah.
Could you explain why? Like where we can see it?
Well, I think if you just plot the fluctuations and do the Y integrations, if you keep this, then it would be some force of that kind. The 10D like 10D scale and word volume. But if you keep the Y factor, there will be some factors of that. So apparently it's a constant, like choosing that. So for GKP it is not important, but for we have taken into account volume modulus, and for volume modulus, there these equation, compact manifold are not fixed completely. They are fixed approximate.
I see.
So that is the analog of volume modulus, and that actually makes it X dependent. Like the not this quantity, but the fluctuation makes X dependent. So at least for those, there will be a space-time dependent part. So we have kept those factors so that finally the constant is not a position dependent. We did not consider the theory where the it's like a space, the coefficient in front of it is others it would be space-time dependent, at least for volume modulus. But for us, you are right, we could have set it to 0. Even the fluctuations we got is also 0. found it later, but we combine the volume modulus.
But
and-
none of the future constraints ever give any limitations as to what your Y factor has to be. We just choose it because we want the right factors for.
Yes, this is the choice, and we have given an expression for that. It's a choice.
Okay.
So that when you deal the volume modulus, these become space-time independent.
I see.
So that's yeah. In GKP, it's not fixed.
Okay, thank you. Anyone else has any?
What's the status of higher derivative corrections in this GQP setup? Are they under control or?
I think in the GKP, not the what I heard and said. So I think in GKP, at least in the sushi case, supersymmetry cases, it's known that this is the tree level. Then the phenomenology community use the word compactification, and anything on top of these are connections and control. But in the non-sushi case, like I did not specify what is the background. One can have a non-sushi RGP which breaks all the sushi, but at least I was giving a talk where string seminars, but then subject setting, he was claiming that the non-sushi case GKP is wrong. That's what his statement. But I don't know, like that time Heveka and many other actually did not agree. So I don't know about the corrections, but my impression is that the sushi case it is, yeah. And I would expect if you add those corrections on top of the actions, then the background also modifies because it gets output corrections. It becomes scalar, but in the so the background get modifies, and then also like the fluctuations on top of that we can, once we know the background, we can take fluctuations and redo this procedure. I would expect that those are corrections. Already at this stage, people are doing direct product compactification, although for terminology purpose, they say that they are working on the word compactification, but computing various stuff, they just take large volume limit. But this is direct product, but for them, our computation should be corrections of alpha price input.
Anyone else have any questions? No, you can thank the speaker again.